Hello everyone, I'll be presenting our work SceneReplica, benchmarking real-world robot manipulation by creating replicable scenes. Benchmarking is a key component to evaluate the frameworks, especially on a common ground. Popular robot manipulation benchmarks like Furniture Bench, Graspa utilize additional setup in the form of AR tags to replicate the scenes, while NAST assembly board is limited only to insertion and threading operations. To this extent, we propose a new benchmark called SceneReplica, which is easier to use and intuitive to set up. SceneReplica consists of cluttered tabletop scenes for the real-world robot testing. There is no requirement for any sort of additional setup to replicate these scenes. SceneReplica consists of YCB object set, which is widely used and hence easier to adapt by the robotic community. We start off by trying to determine the approximate reachable space of the robot system. We spawn the robot and several grid points in simulation and remove any grid points that doesn't have a valid motion plan to it, essentially leaving us with the approximate reachable space of the robot platform. Once the reachable space has been determined, we then proceed to spawn the objects in their stable poses without collision but with certain degree of occlusion. Here are the set of 20 scenes that have been chosen after carefully examining for diversity and frequency of object occurrences. Here is how we set up the scenes in the real world. Once the camera pose has been fixed, a reference image is rendered and overlaid onto the real world camera feed. As the user tries to align the objects with the overlaid image, the intensity of the overlaid part changes, visually indicating the user how much the object has been aligned. Using this feedback, user can try to align all the objects one after the other, thereby replicating the scene easily. Here is a short demo of how the scene replication happens. User utilizes this visual feedback of the intensity change to align these objects, which doesn't require any sort of additional setup and can be done pretty quickly. We primarily evaluate SceneReplica on three kinds of pipelines: model-based grasping pipeline, model-free grasping pipeline, and an end-to-end learning-based grasping pipeline. In model-based grasping pipeline, the perception component tries to estimate the 60 object pose, and from an offline grasp database, a motion plan tries to generate a valid feasible plan to each of these grasps, and when a valid plan is found, the system then proceeds to grasp and drop off the object. In a model-free grasping pipeline, the system doesn't have the knowledge of 3D models of the objects, so the perception component deals with the unseen object segmentation. Once the segments have been obtained, a grasping component utilizes the 3D point cloud along with this segment and tries to generate the possible grasp. As above, a motion planner tries to check a valid motion plan to each of the grasp, and when a valid motion plan is found, it then proceeds to grasp and drop off the object. We evaluate DexNet 2.0 as the end-to-end learning-based grasping pipeline. DexNet takes in the scene data and then directly outputs the grasp that needs to be executed by the robot platform. A motion planner checks if a valid motion plan can be found, and if a valid motion plan is found, it then proceeds to grasp and drop off the object. Here is a short demo of model-based grasping that we implemented using GDR NPP as the perception component, grasp it as the grasping planner, and move it as the motion planner. As you can see, the poses are being estimated and the motion planner continuously tries to plan to pick up these objects. Here is a demo of model-free grasping that we implemented using MSM Former as the perception component, contact GraspNet as the grasp planner, and move it as the motion planner. Here is a short demo of DexNet 2.0 grasping pipeline. DexNet 2.0 directly predicts the grasp that needs to be selected and executed by the robot platform. In total, we evaluated SceneReplica on 3 kinds of model-based grasping pipelines, 5 kinds of model-free grasping-based pipelines, and 1 end-to-end learning-based grasping-based pipelines, and 1 pipeline with the ground truth object poses. We evaluate all these pipelines using 2 metrics: pick and place success and grasping success. Grasping success is when the object has been successfully grasped. Pick and place success is when the object has been successfully dropped off. Coming to the failure case in SceneReplica, we classify these failures primarily into 3 categories: perception failure, planning failure, and execution failure. A perception failure is when the grasp fails due to error in perception. Perception failures in model-based pipelines occur primarily when there is no pose estimation or if the perception error is greater than the threshold. We evaluate the perception error in model-based methods using the ADDS metric with 10% of the object's model diameter as a threshold. Similarly, in model free pipelines, a perception failure occurs when there is no segmentation or if that perception error is greater than the threshold. We evaluate the perception error using overlap F measure with 75% as the threshold. Coming to the planning failure, there are two kinds of planning failures. One is due to the motion planning, the other is due to grasp planning. When no valid grasp is found to grasp the object, we treat that as a grasp planning error. And when a valid grasp has been found, but yet the system fails to grasp the object, we call this as motion planning error. Execution failure, we call this as post grasping operations. Once the object has been grasped, we then proceed to lift the object, rotate the gripper by 30 degrees, translate it straight ahead, move to the drop off location and drop off the object. If the pipeline fails at any stage of these, we consider it as the execution failure. Here is an example picture depicting the execution error, where the robot grasped the object but failed to lift it. Finally, we can evaluate SceneReplica on various kinds of robot manipulator systems. All you need to do is determine the reachable space of the new robot manipulator system. Using the SceneReplica ground truth, spawn the objects in the reachable space of the platform. Adjust the camera pose as needed so all the objects are in the field of view of the robot. Once the camera pose has been adjusted as needed, we can render the reference image using the camera extrinsic parameters. To conclude, we proposed a easy to use benchmark for the robot manipulation, which can be used with various kinds of robot platforms and for different camera settings. We evaluated SceneReplica on model-based grasping, model-free grasping, and end-to-end grasping pipelines. We try to continuously evaluate other methods and add to our benchmark leaderboard, and we also plan to evaluate SceneReplica on various reinforcement learning methods. Thank you.